Okay, so let me remind you of the recursive definition of rooted binary trees. So RBT. Okay. And okay, so you know the base case is the empty tree. So the empty tree is a rooted binary tree. Okay. And you know now comes the interesting case that if you have two rooted binary trees, T1 and T2 are rooted binary trees. And so what we do is we represent T1 and T2 sort of, as these structures that look like trees. Okay, and they have roots, so these special guys which we call the root. Okay, then when you join roots to a new root gives a new RBT. Okay, now it's important when I say that T1 and T2 are rooted binary trees, what we really mean is that they're disjoint rooted binary trees. So if you think about constructing a rooted binary tree with some people in here and some of those people also in here, then this definition doesn't work. These are disjoint rooted binary trees. So I mean, I don't need to say that. So all the circles, all the vertices, all the nodes in these two trees are distinct. So we use the word disjoint for that. Okay, so this means that the constructor rule takes these two guys and produces, the following tree, T1, T2. So it's ordered. So the order matters. If you start with T2 and T1, you get the flipped version, the reversed version of this. And so that's a different tree in general. Now, these roots are no longer roots. Okay? And they both connect to the new root. Okay, so this is a new root. Okay, good. Okay, so this is the constructor. Now, so let's have a look at some trees. Okay, so we've got epsilon. Okay, now this guy can give you, just a root. Okay, and from this root, we can get, we can add, this guy can be T1 and T2. So from this guy, we can certainly get this guy. Okay. You put this guy as T1, this guy as T2, and connect them to a new root. And from this guy, we can certainly get, we can make this T1 and this T2, and we can get a new root, okay, connected to this guy, and connected to this guy on the other side, okay. And if we wanted to, let's do one more. We can make this guy T1 and this guy T2. So let's see what that gives us. So it's going to be complicated. This guy is T1, so that's going to give us. This guy is T2, so that's going to give us. Wow, look at that beautiful tree. Woo! Okay, now what I want to do. Okay, so this guy is an empty tree. So, it's not a very interesting tree. But, once we get to the non-empty trees, let's look at the number of circles. Sometimes we call this the number of vertices or the number of nodes. The number of circles, and let's look at the number of links. So here are the circles. Okay, so nodes, or let's call them vertices. Okay, and links. Okay, so vertices here is 1, links 0. Vertices here is 3, links 2. Vertices here is 1, 2, 3, 4, 5. Okay, links 1, 2, 3, 4, 4. Vertices here is 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 vertices. And links 1, 2, 3, 4, 5, 6, 7, 8. 8. Ah, lots of nice tinkering. Okay. We should observe, if you have your tinkering hat on, that, look, the number of links is always 1 less than the number of vertices. Okay, even for this very complicated tree, this simple guy, okay, and that's in fact true in general. Okay, so every rooted binary tree, so everything that's constructed in this way, okay, as long as it's not empty, has a number of links which is 1 less than the number of vertices. So I'll claim every non-empty rooted binary tree has a number of links equal to number of vertices minus 1. So we're claiming a property of rooted binary trees. Okay? So structural induction, because this is a recursively defined set. I try to prove that everything in this set has some property, structural induction. So let's look at the base cases. So the base case. So is this property true for the base case? Base case. The empty tree. That's interesting. Okay. Because this claim is a claim that requires a certain property of every non-empty rooted binary tree. So since this is empty, the claim is vacuously true. It's trivially true. Okay? Because this condition only needs to hold for the non-empty guy. Okay? So for the empty guy, the claim holds. Okay? Now what we need to do is we need to prove that the constructor, the way of creating new trees, preserves that property. Okay? That, you can think of this as a property. So the next step, the induction step, okay, the way of creating new trees preserves, so I'm going to underline preserves. It's very important to sort of realize the importance of that word preserves. Okay, the way of creating new trees preserves the property. Okay, and we're going to consider four cases. Okay, of this constructor. Okay, so 4 cases. I'm going to show that the way of creating new trees preserves this property. And why am I considering 4 cases? Because, the 4 cases depend on whether any of these parent trees are empty. The property holds for parent trees, but the parent trees are sort of special. If they're empty, they're sort of special. Okay, so 4 cases. And so let me tell you what the 4 cases are. So the 4 cases are T1 equals the empty guy, T2 equals the empty guy. So that could certainly be the parents, okay, that are going to create a new child, and these 2 parents have the property vacuously, but they have the property. So I need to show that the child is a single node and that single node has the property. Well, in the single node is what we just considered here. Vertices 1, links 0, so check. Okay. Now I could have the other 2 cases where T1 is equal to the is empty and T2 is not empty. Okay, and they satisfy this property. Okay, and the other case is that T1 is not equal to the empty tree, and T2 is the empty tree. Okay, so that's the other case. Okay, and then the 4th case is where they're both not empty. T1 is not equal to empty tree, and T2 is also not equal to the empty tree. Okay, so let's consider this case. Okay, so T1 is the empty tree. So what's the picture? The picture is like this. T1 is the empty tree, so you have the new root. The child that's created is a root that's connected on the left to nothing, but on the right, we have T2. Okay, what's the picture here? The picture here is the child. So I have to prove that this property is preserved. So we have the child, okay, and now T1 is not empty, so you have a real tree here, T1, okay, but T2 is empty, so there's nothing on that side. And in this case, the child that's created has what's called a left subtree, which I'll call, which is T1, and what's called a right subtree, which is T2. But you don't need to, remember these names. I'm just showing you the picture of what's going on. Okay. So in all these cases, let's count up the number of vertices and the number of links. So the number of vertices is, so in this case, okay, the number of vertices is equal to, okay, 1, the new vertex, plus however many vertices are in T2. So it's 1 plus however many vertices are in T2. So let me call that, N2. Okay, so this is the number of vertices in T2. What about the number of links? The number of links is 1 plus however many links are in T2. So it's equal to 1 plus however many links are in T2, let me call that L2. So L2, number of links in T2. Okay. But I know, so I know that the number of links So I know that so I want to show that the number of vertices is equal to 1 plus the number of links. Okay? So I want to show that 1 plus n2 is equal to 1 plus L2 plus 1. Want to show. Okay? Want to show this. So let's show that. So 1 plus n2 is equal to, but because this parent has the property, it's equal to 1 plus, so L2, n2 is L2 plus 1. L2 plus 1. Because the parent had the property. And if you compare this to this, you see it's exactly what I wanted to show. The number of vertices, okay, is equal to 1 plus the number of new links. Okay? So, in this case, I've proved that the property holds. Okay, so the property is preserved. Okay, what about in this case? Very similar. Let's count up the number of vertices. So number of vertices is equal to 1 plus n1. 1 plus n1, where n1 is the number of vertices in T1. Number vertices in T1. Okay, and how many links? It's 1 plus the number of links in T1. Number of links equals 1 plus L1. And the same argument, n1 is equal to L1 plus 1. So this is equal to 1 plus L1 plus 1. Okay, why? Because n1 is equal to L1 plus 1. The number of vertices in T1, because the parent has the property, is 1 plus the number of links. So 1 plus L1 plus 1. 1 plus L1 plus 1. But that's exactly 1 plus the number of new links. So the property is preserved. Okay, so the property is preserved. Is preserved. This is the most complicated case, so let's analyze that slowly. Okay, so let's just count up for the child. Okay, how many links and how many vertices? Number of vertices is equal to 1 plus n1 plus n2. 1 plus n1 plus n2. Okay. The number of links is equal to 2. So there are 2 new links plus however many there were in L1 plus however many there were in L2. So it's 2 plus L1 plus L2. Number of links in tree 1 plus the number of links in tree 2. Okay. So it would be great if this number of vertices is 1 plus that number of links. Okay, but we know that N1 equals L1 plus 1. N2 equals L2 plus 1. Because we're only trying to show that the property is preserved. So we only need to consider the situation where the parents have the property. Okay? So what's the property? The property is that, the number of vertices is 1 plus the number of links. The number of vertices is 1 plus the number of links for both the parents. The number of vertices is 1 plus the number of links. Okay? In this case, here, this is 1 plus L1 plus 1 plus L2 plus 1. 1 plus L1 plus 1 plus L2 plus 1, which is equal to 3 plus L1 plus L2. So that's 1 more than the number of links. So the property is preserved. Property is preserved. Okay, so this has been a slightly complicated structural induction. Because it's involving a more complicated recursive definition of a structure, the rooted binary tree. What we have shown, the primordial ancestor, the base case has the property, and the method of creating new trees, okay, no matter what the parents are, as long as the parents satisfy the property is preserved in the child. That's all you need to conclude by induction, more specifically structural induction, that this property holds for all rooted binary trees. By induction, okay, for any non-empty rooted binary tree, the number of vertices equals the number of links plus 1. Fundamental property of trees, and we have proved it with structural induction. In any rooted binary tree, okay, you have one less link than vertices. Okay, so, that's the end of the lecture. Let me summarize a little bit structural induction. Okay, so let me erase and summarize. Quick application of the result we just proved. Remember this tree I showed you last time? I'll draw it again. I drew this tree, and then I added one more link, and I claimed that this tree is not, this structure is not a rooted binary tree. And then we thought, wow, how could we show that? Because, when we want to show that something is a rooted binary tree, we give a derivation. To show that this is not a rooted binary tree, we have to show that no possible derivation can end up with this structure. Are we sure? There are so many ways to do derivations with that recursively defined, rooted binary tree, that definition. You can derive this way, you can derive that way. Are we sure none of them produce this? Now we have the tool to rigorously show that this cannot be a rooted binary tree. Okay? And, it's very simple actually. Let's count up the vertices. Number of vertices equals 1, 2, 3, 4, 5, 6, 7, 8 plus 4, 12 plus 3, 15. 15. Number of links equals 1, 2, 3, 4, 5, 6, 7, 8 plus 5 plus 2. Again, 15. Okay. But for every rooted binary tree, we just proved using structural induction that the number of links must equal the number of vertices minus 1. And in this case, that property is violated. This is not equal to the number of vertices minus 1. And our structural induction proof is rigorous. So every rooted binary tree must have that property. So this cannot be a rooted binary tree. We don't need to consider all possible derivations. We have shown that it violates a property that all rooted binary trees have. That's the power of structural induction, to allow us to prove that property. Okay, let's erase this. And I will be right back. Okay, so structural induction. It's very important for computer scientists. So is induction, by the way. And anyway, structural induction is induction is induction is induction. Induction is induction is induction. But structural induction is very important for computer scientists because, we build data structures. We build objects. We put them in memory. We run algorithms on them. Okay? And we want to prove that, for example, every structure that we build has some property. For example, when you talk about balanced trees, you want to show that every balanced tree has this property of balance, and so on and so forth. Okay, so it's fantastic that we build all these things, but it's even better if we can prove properties about the things we build. Okay? So structural induction is very important. Okay, so structural induction applies when you have a recursive definition of some set. So you have a recursive definition. Okay, so recursive set. Okay, now you have some property that you want to prove about all elements of the set. So you have some property. Let's call this set S. You have some property, let's call it P. You wish to prove about everything in S. Okay. So, it's typical in a recursive definition, you have the primordial elements, okay, the base cases. So prove, you show P, you show your property for the primordial elements. These are the base cases in S. Okay, then you prove that, the way you construct new elements, the constructors, the way you procreate, prove that, the constructors. So the way you procreate, the procreation preserves the property S in the child. So this property S is inherited. Okay, so procreation preserves the property P in the child. Okay, that's created. Okay. And if you can show that, if you can show the primordial ancestors have blue eyes, and if you can show that blue eyes are inherited whenever the parents have blue eyes, bam! That's it, you're done. Okay. By structural induction, all the orcs have blue eyes. Everything in S has that property P. Important. I'll put it in red, and I'll put a big check mark. Structural induction is not for showing that everything with a property P is in S. Okay. So it's not for showing that everything with some property is in S. Okay. You need other techniques, well-ordering principle, and usually more sophisticated arguments. So structural induction can be used to show that all leopards have 4 legs. Structural induction cannot be used to show that all creatures with 4 legs are leopards. Okay. Structural induction can be used to show that all RBTs have, a number of links which is 1 less than the number of vertices. It cannot be used to show that all graphs in which the number of links is 1 less than the number of vertices is an RBT. Okay. And so on and so forth. So it's very important that you distinguish these two types of questions. So distinguish those. Very important that you distinguish those. Okay? So see you next time.